Hello students, today we are going to learn about what is colligative properties. Colligative properties are the physical properties which will depend only on the number of solute particles and not on its nature. In this chapter, we are going to discuss about the colligative properties of a solution. The solution is produced by adding some amount of non-volatile solute in a volatile solvent. For example, I am preparing a salt solution. So salt forms the solute. So salt, what type of substance is salt? It is a non-volatile solute. And water is taken as the solvent. So what type of substance is water? It is a volatile solvent. So when salt is added to water, what all changes happen? Here, first thing that we notice here is the change in vapor pressure. So what do you understand by vapor pressure? To understand better about vapor pressure, I have taken two beakers. In one, I am filling it with pure water. So water is made up of many water molecules. So on the surface, you find many water molecules are there. So what is special about water? Water is a volatile liquid. So evidently, all the molecules that are present on the surface is capable of changing into vapors. So you find that these vapors will be present over the solution or over the liquid. So as a result, when it is in the closed container, you find that, so suppose it is a closed container in which you have taken the pure water, you find that all the molecules that are present on the surface will change into vapors, and these vapors will exert a pressure downwards. So that pressure that is exerted by the vapors on the surface of the liquid, that is known as vapor pressure. So here in the case of water, you find that the vapor pressure is taken as P0A. Now I'm adding some amount of salt in it. So what happens here? On adding salt, you find that some molecules of salt will be occupying here and there. So the number of water molecules that are present on the surface will evidently decrease. You know that salt will not be changing into vapor. It is a non-volatile substance. So as a result, the vapors that are produced from the surface will decrease. With the result, what happens is the vapor pressure of the solution is found to be less than that of the pure water. So in salt solution, you find that the vapor pressure will be always less than that, and that is denoted by PA. Now that we have understood that P0A is the vapor pressure of the pure solvent and PA is the pressure of the solution, you find that P0A is always greater than PA. Also, for solutions, you have learned that Raoult's law is applicable and PA can be written as P0A into XA. What is the change that is happening when a non-volatile solute is added? So you find that the change in vapor pressure is found out by subtracting PA from P0A. P0A minus PA is equal to P0A, and you know that PA is P0A into XA. So then the change in vapor pressure becomes equal to P0A can be taken outside and we get 1 minus XA. That is, change in vapor pressure delta P is equal to P0A minus PA, which is equal to P0A into 1 minus XA. We know that for binary solutions, XA plus XB is equal to 1. That means delta P is equal to P0A into 1 minus XA can be rewritten as P0A into XB. Delta P, we know it is P0A minus PA. That is P0A minus PA divided by P0A is equal to XB. So what does it mean? Relative lowering of vapor pressure is equal to the mole fraction of the solute. Since it is dependent only on the number of solute particles and not on its nature, relative lowering of vapor pressure is considered as a colligative property. You have seen the change when salt is added to water. Vapor pressure decreases considerably. Now we are going to discuss about what is boiling point. What do you understand by boiling point? In lower classes you have learned that the temperature at which the liquid starts boiling. What is actually happening during the process of boiling? That we will see now. When the liquid starts boiling, you find that there is maximum amount of vapor pressure produced. When the vapor pressure becomes equal to the atmospheric pressure, the liquid starts boiling. What happens to the boiling point of the solution when a non-volatile solute is added? Here, to discuss that, we have to plot a graph against vapor pressure and temperature. I'm going to plot the graph of vapor pressure against temperature in order to understand what happens to the boiling point when a non-volatile solute is added to the solvent. For which I'll take vapor pressure on the y-axis and temperature on the x-axis. Now, suppose we are taking pure water. So, water is the solvent. When we try to check the vapor pressure, you find that at room temperature, let this be the vapor pressure of the liquid. Now, as we heat the liquid, you find that vapors also increase. When vapors increase, vapor pressure also will increase. So then the plot of the graph will go like an exponential curve. And you find that at the particular temperature, you find it will reach the 1 atmosphere mark. So the liquid is set to boil when it reaches the 1 atmosphere mark. So let this be the 1 atmosphere mark. So you find that at the point T 0B, we say that the pure water starts boiling. So that becomes the boiling point of water. So for pure water, it is found to be 100 degree Celsius. So I'll mark it as pure solvent. We have seen earlier that on addition of salt, the amount of vapors in the solution will decrease considerably. As a result, you find that the vapor pressure decreases. So then, if you are taking the salt solution, the vapor pressure of the solution is always less than that of the pure solvent. And when we heat the solution, you find that vapors will increase. So it will gradually increase, and you find that by the time the pure water has started boiling, or the pure solvent has started boiling, it hasn't reached the 1 atmosphere mark. So then you will have to heat it further when it reaches 1 atmosphere mark. So you find that the corresponding temperature is always greater than the first one, and that can be marked as TB. So the change happening here is when we are adding a non-volatile solute in the solvent, the vapor pressure decreases, with the result the boiling point of the solution will increase. That is, there is an elevation in boiling point. What is the change in the boiling point here? That can be understood from the difference here, that is TB minus T0B. That can be marked as delta TB. Now, how is it related? So, mathematically speaking, you can say that delta TB is proportional to the amount of solute that is added in the solvent. So you find that it is proportional to the concentration of the solution, and it is given in molality. So delta TB is proportional to molality, or you can equate it to delta TB is equal to Kb into M, where Kb is known as the molal elevation constant, otherwise known as ebullioscopic constant. Kb is known as ebullioscopic constant. Now, what is the value for M? We know that delta TB is equal to Kb into M is 1000 WB by MB into WA. So this expression helps to understand the change in the boiling point when a non-volatile solute is added to the solvent. Here too, you find that the change in the boiling point is dependent only on the amount of the solute that is dissolved in the solvent and not on its nature. So this elevation in boiling point is also an example for colligative property. Have a closer look at the diagram. Here you find that the vapor pressure of the pure solvent is always greater than that of the corresponding solution where we have added a non-volatile solute. So you find that the change in vapor pressure is always given as delta TB is proportional to molality. Delta TB is Kb into M. Delta TB is nothing but Kb into 1000 WB by MB into WA, where Kb stands for the constant which is known as ebullioscopic constant. Have you ever wondered whether salt solution or pure water will freeze easily? To get the answer, first we should understand what is freezing point. Now, what do you understand by freezing point? Freezing point of a liquid is the temperature at which the liquid starts solidification. How to measure the freezing point of a liquid? We are taking the liquid and starting to cool it down and noting down the vapor pressure, for which we need to draw the vapor pressure temperature graph. I am drawing temperature on the x-axis and vapor pressure on the y-axis. Here we begin with a liquid. So suppose this is the point of vapor pressure of the pure liquid. I have taken water for example. Now I start decreasing the temperature. We are cooling down the liquid. What happens on cooling? You find that condensation occurs, vapors will lose their energy. It will start condensing. As a result, vapor pressure will keep on decreasing. So you find that it gradually decreases till it reaches a particular point. So at a particular point, you find that it will change its slope. So it has a break in the curve and it starts cooling rapidly. So this particular point is known as the freezing point of that liquid. So what is meant by freezing point? Freezing point of a liquid is identified as the particular temperature at which the liquid coexists with the solid, and that can be identified from the break in the curve. So let this be T0F for pure water. We repeat the same experiment with some salt solution. So the salt solution will have vapors less than that of the pure solvent. So vapor pressure of the solution is always less than that of the solvent. So here on cooling this, you find that vapors condense. As a result, vapor pressure decreases and you find that it will gradually decrease, and the moment you find that it has reached T0F, it is still in the liquid state itself, but when it is cooled further, you find that it joins the curve which will show the solidification. So you find that the temperature corresponding to that is lower than the first case, and that can be marked as TF. So what is the change in temperature? Change in temperature can be marked as delta TF, which is again proportional to the amount of salt that is dissolved, and that is equal to the molality. That is, delta TF is proportional to molality. Delta TF is equal to Kf into molality, where Kf is known as the molal depression constant, otherwise known as cryoscopic constant. So the equation can be rewritten as delta TF is equal to Kf into 1000 WB by MB into WA. Here too, you find that the change in the freezing point or depression in the freezing point is dependent only on the number of solute particles and not on its nature. So this is also a colligative property. The next point for discussion is known as osmosis. So what is meant by osmosis? To understand that, we are just drawing a beaker. We are just doing an experimental setup where we have a beaker and a tissue funnel. Tissue funnel. I take some salt solution inside a tissue funnel which is separated from a beaker full of water. So inside the tissue funnel, you find that there is some salt solution. It is separated from water using a semi-permeable membrane like cellophane. So what do you understand by a semi-permeable membrane? Semi-permeable membrane is a membrane which allows only the solvent molecules to pass through. So we have a solution, salt solution inside the tissue funnel, and it is separated from water outside. So what do you understand by osmosis? Osmosis is a movement of solvent molecules from a region of higher concentration to a region of lower concentration. So which are the solvent molecules here? You find that water present outside the tissue funnel forms the solvent molecules. So solvent concentration is more outside, and so the water molecule starts gushing in through the semi-permeable membrane. So with the result, what happens? You find that this was the initial level of the salt solution before osmosis, and after osmosis you find that the level of salt solution will rise up. So osmosis is the process of movement of solvent molecules from a region of higher concentration to a region of lower concentration through a semi-permeable membrane. We are concerned with understanding what is meant by osmotic pressure. It is the pressure exerted on the solution side in order to stop the process of osmosis. So you find that the pressure exerted on the solution side, that is the hydrostatic pressure applied on the solution side in order to just stop the process of osmosis, that is known as osmotic pressure. And osmotic pressure is represented by the letter pi. So pi doesn't denote the pi value, that is 22/7. It is just the representation of osmotic pressure. Now, what all factors are affecting this osmotic pressure? You find that osmotic pressure is dependent on the concentration of the solution. It is also dependent upon the temperature. So you can combine it together and write it as pi is proportional to Ct, where C stands for the molarity or the concentration of the solution and T is the temperature in Kelvin. So pi is equal to RCT, where R is the universal gas constant. Now converting the value for molarity, you have pi is equal to R into number of moles of the solute per liter of the solution into temperature. which can be rewritten as pi V is equal to NBRT. This is known as the Van Hoff's equation for osmotic pressure, and this is a peculiar equation which fetched the first Nobel Prize in Chemistry for Van Hoff. Pi represents the osmotic pressure, V is the volume of the solution, Nb is the number of moles of the solute, R is the universal gas constant, and T is the absolute temperature. Here too you find that it is dependent only on the number of solute particles and not on its nature. So osmotic pressure is again a colligative property. So this video gives an idea about all the colligative properties for solutions. Osmotic pressure has a wide range of application. The most important one is the case in medical field. Medicos dilute the intravenous injections using saline water. Why is it done? You find that 0.91% saline solution is having the same osmotic pressure with that of the human blood. So before administering the injections are to be diluted with 0.91% saline solution. Otherwise, you find that there is osmotic pressure variations, and that may lead to bulging or shrinkage of the cells. Thank you.